Hello and welcome to week 7 live session of NPTEL 7 Semiconductor Device Modeling and Simulation course. I am Om Maheshwari and today we will be solving some questions that may help you in your exams. So in this week we will be studying about uh, semi-classical transport theory mainly. We'll look at the distribution function, Boltzmann transport equation, relaxation time approximation, and scattering and mobility related questions. So let's start. The first question is, in semi-classical transport, electrons in a crystal lattice are represented as. Correct. So when we are assuming some EK, here we consider the wave nature uh, of the particle by solving the proper Schrodinger equation. But for semi-classical transport, what we do is we assume the electron as a particle with some effective mass m star, and we say that this m star has inscribed all its wave nature, and then we use Newton's laws to uh, to calculate the transport. So in this way, the wave nature is considered only through the effective mass. So that is why it is called semi-classical transport. Okay, see the next question. How does an increase in temperature affect the Fermi-Dirac distribution function? Somnath, do you know this answer? I muted you because of the noise. Can unmute and answer? Yeah. So this we have seen before also. So okay? So what is the Fermi-Dirac distribution? F of E is uh, correct. So at zero temperature, this is EF, this is the one probability we have. As temperature increases, this function becomes broader. Yeah, here it will have value. Okay, what is the significance of introducing quasi-Fermi levels? A, to simplify the mathematical calculations. Yeah. B, to model the carrier concentrations under non-equilibrium condition. C, to increase the band gap of semiconductor. D, to reduce the temperature dependency of carriers. So it is to model the carrier concentration in non-equilibrium conditions. This you might have seen in a PN diode when you apply some forward bias. The band diagram, if this was the band diagram in equilibrium, in non-equilibrium, it will become something like this. And EFP, sorry, FM, EFP, here it was a single Fermi level. Now the Fermi level has split. And on each side, the carrier concentration can be found using EFN and EFP. Okay, next one. What happens to the displaced Maxwellian function when the electric field is applied in a specific direction? Yes. So in equilibrium, if your uh, distribution function, let's say, is something like this, both, yeah, so with electric field, distribution shifts its peak such that you get some net current. Okay. Yeah, I was just explaining the function becomes asymmetric. So this is the equilibrium condition. And when you have applied some electric field, this there will be shift in the shift in the position of the center of this maximum of the distribution function, and it will become asymmetric. Okay. Okay. Next question is, what does Liouville theorem state about distribution function along a particle trajectory? So Liouville theorem states that the distribution function along a particle trajectory, its derivative when becomes zero. Is option C. Basically, del by del f r k t by del t is zero. This is Lewis theorem. Okay, next. Yes, yes, right. So to calculate this, we get 1 by mu is 1 by mu 1 plus mu 2. Where does this come from? So mu, as we know, is P tau by m. And with relaxation time approximation, when we solve the scattering rate, we get tau is equals to 1 by tau 1 plus 1 by tau 2. From here, we get this 1 by mu is 1 by mu 1 plus 1 by mu 2. And this is also called Matheson's rule. I don't remember the spelling, but something like that. So it will be 1 by 300. Yes, 1 by 150, which will be 3 by 300. It will take the LCM, and which will finally be mu is 100 centimeters square per volt second, average mobility. Next one. Yes. Okay. So how do we get this? Is we know this. We know now. We know that the energy gap between donor energy level and Fermi level is 0.036 electron volt. So we can say the probability of finding electrons at energy of donor level ED that we can find f of ed is 1 upon 1 plus exponential of 0.036 kTyq. Let me I will assume to be 0.026 at room temperature. If I solve this, it will be 20, zero point 0.2. So this is the probability of finding electrons at donor level. Now we have to find the dopant atoms at ionized at 300 Kelvin. So these are what? These will be the ionized one. So the ionized probability of ionized atoms will be 1 minus P donor 0.8 or 80%. This clear? Next one. Right. For a Kirchhoff phonon, it is root T. King for yeah. This is a 1 by root T. So your answer is D. Next one. Yes. Yes. It's Bose-Einstein distribution. For electrons, we use either Fermi-Dirac or Maxwell-Boltzmann. For phonons, we use Bose-Einstein distribution. Yeah, we can use both. Maxwell-Boltzmann is again under approximation for non-degenerate. But Fermi-Dirac is always valid, but Fermi-Dirac is difficult to calculate, so we sometimes tend to use Maxwell-Boltzmann. So whatever we are studying here, this is particle nature, right? In semi-classical transport. Okay. Which of the following is not an assumption made in Boltzmann transport equation? Right. So option B is correct. Uh, okay, so give me a minute. So if you remember from the video, the Boltzmann transport equation is del F by del T plus V del F plus E by choice del Q of K is uh, some of, I'll just write scattering terms here. So here are a few terms here. So this is our uh, del F by del T. This is a distribution function that we are perturbing with time. This is the diffusion term, diffusion of particles. This is the drift of particles. Or let's say, let me just call it electron for now. This is diffusion of particles due to some gradient in the with position of the particles. Then only particles will diffuse. And this is the drift of particles due to application of external electric field. The particles will drift. So this is due to the drift of particles. Now here on right hand side, whatever is left is due to the collisions, the interaction of particles uh, with the lattice or any all the different kind of scattering interactions. Now the assumptions this is based on is assumptions when this is derived is first of all is semi-classical transport. which is effective mass approximation. Second is instantaneous collisions. Third is no dependence on initial conditions, which is basically means there is no memory effect. So basically what this assumption means is like at any instant there's no dependence of the party on the previous state of the particle. How the particle was behaving previously, it does not affect the current state uh, of the particle. So that is why uh, there is no memory is considered. We don't know what particle was behaving earlier, and we it does not affect its present state. So that's why collisions have a memory effect. This is an incorrect assumption. This is not an assumption. Collision do not have a memory effect. That is what we assume here. Is this okay? Okay. Next, what does the semi-classical transport theory primarily describe? The answer is option C. The motion of carriers in crystal lattice under the influence of electric and magnetic fields. Next question. Which of the following is a key assumption in semi-classical transport theory? A. Electrons behave as particles in real space and waves in momentum space. B. Electrons always move in straight lines inside the crystal. C. The influence of periodic potential is completely ignored. D. The electrons interact strongly with one another. Yes, yes, you are audible. So I was from where did you lost your connection? Yes. So it has no dependence on initial conditions or any state of the particle that was we do not know what was the state of the particle previously. And based on that assumption, yeah, sorry, okay, yeah, yeah, yeah. External forces are constant over a certain. No, this is not about diffusion length. External forces do not describe diffusion. Will describe diffusion length. This is electric field. Yeah. Yes, yes, yes. Which of the following is a key assumption in semi-classical transport theory? Because again, we have seen this. Is option A. Right. Okay. In the semi-classical transport theory, right, the group velocity of the electron is determined by the slope of the energy band k space. So if you have an EK diagram like this, the velocity, okay, so we know E is h cross square k square by 2m. So we do dE by dk, it will be h cross square k by m, and 1 by h cross. If you take this one h cross, move it to the LHS, del E by del k will be h cross square k by m, which is p by m, which is v. So your velocity is dependent on the slope of EK. Okay, so one question I want to ask you. Let's say you have an EK diagram like this. Something like this. Let's say point A, B, and C. So can you tell me among A, B, and C which will have the highest effective mass of electron? Effective mass of electron. Yeah. Right. B is correct. and YB. Yeah. Okay. So what is effective mass? It is h cross by del 2E by del K square. So it is like the rate of change of slope. Or yes. Okay. So one more question. Uh, will the effective mass at C will be positive, negative, zero? What will it be? No. Effective mass at C will be negative for electron. Yeah. C. Yes. So this you can understand using this also. P equals to h cross square k square by 2m. So let me call it, consider this whole thing in a one constant a. E equals to a times k square. Or this is similar to y equals to a x square. Some parabola equation. Now when a is negative, then only you can have a parabola like this. Y equals to minus, let's say, 5 x square or something like that. So it has to be negative for the parabola to be like this. And if we consider these two cases, this one and this one, so here it could be y equals to, let's say, 10x square, or y here it could be y equal to 5x square. Now why 10x square? Because here with small change in your x, there is a large change in y. That's why this coefficient has to be higher. And this coefficient mean is higher, that means h square square by 2m is higher, that means m is lower for this one. Similarly, m will be higher for this one. So this is also called parabolic mass approximation, and you can use this parabola theory if you get some questions like this to compare the effective masses. Yeah, this theory of parabolic effective mass, like trying to fit a parabola to determine the relations between different effective masses at different points. Okay, what is the significance of relaxation time approximation in semi-classical transport theory? Right. Okay. In the presence of both electric and magnetic fields, which force governs the motion of carriers? Right. What is Lorentz force? This is Lorentz force. This is electric field, and this is magnetic field and velocity. Next one. What is the primary limitation of semi-classical transport theory? Right. And what does this mean? Which effects does it fail to capture? What are the quantum mechanical effects? Okay. So, right. Uh, if you have seen like solutions to when you do solutions of Schrodinger equation for finite potential well, so then you see the concept of tunneling also. The wave functions penetrate through your uh, boundary edges also when the potential is finite. So this happens in real devices also. So this basically there are two things which it fails to capture. One is tunneling, which we do see in real devices, the tunneling phenomena when the barriers are very thin. And second one is quantum mechanical confinement. So quantum mechanical confinement QMC effects are some other effects which basically adjust the energy levels as the semiconductor becomes thinner and thinner, such that the threshold voltage of the transistor increase and many other effects are seen. And it affects both the density of states, mobility, threshold voltage. A lot of things are affected. So this is not considered in the semi-classical theory. Okay. So last question. How does scattering influence the carrier mobility in a semiconductor? A. Increases mobility by providing additional energy to carriers. B. Decreases mobility by reducing the mean free path and relaxation time. C. Has no effect on mobility. D. Alters the crystal structure permanently. No, it's B. So the whole concept of mobility comes through scattering only, right? We do not. Uh, so what is scattering? Scattering is some uh, some external influence that is changing the uh, flow of electrons, right? And we define it in terms of let's say in case of metals, we define it in terms of resistivity, conductivity, both which relate to mobility of the electrons or holes. So all whatever relaxation time approximation and everything that was done in the videos was to determine the mobility at the end. Okay, so these are all the questions I had for today. There were a lot of, sorry. Hmm. Yes, yes. We saw it. Mu equals to E tau by M. This is relaxation time. This is mobility. And mean free path and tau have yeah, inverse proportionality. So mean free path basically means how long the electron can go without scattering. And tau is relaxation time is like the time between two scattering events. Okay, so we had a lot of theoretical questions today, so we are finishing early. So if there are no other doubts, we can close the session. And next session will be on Monday. This week I had to reschedule because I was not feeling well. But next session we will have week 8 session on Monday only. No, no, I take my session on Monday. Yeah. Yes, Monday 6 to 8. That is the yeah, that is the usual. Yeah, we will discuss week 8 problems there. Yeah. Uh, it will be difficult to summarize everything. Like okay, so what I'll do next time, I'll try to at the end of each assignment, I'll try to include some questions from previous uh, weeks. Okay, no, just a minute.